Hi guys. So in this one, we're going to be looking at Achieve section 5.1, problems 21 through 29. So 21 here gives us the summation of 19i over n to the second. Now, in my summations, I always use a lower script n. They tend to use a capital N in this section. I'm not quite sure why. I think it's really bad notation. Most everyone always uses lowercase n. Doesn't matter though. So we're looking at the limit as n approaches infinity of the summation from 1 to n of 19i over n squared. Now, I already know that my rules of summations enable me to factor out anything other than the index factor. So the very first thing I did here is I pulled that 19 over n squared out. And then by formula, I know that the summation of I is equal to n times n plus 1 over 2. So, and I forgot to put my limit in, so I had to scrunch it in there. We have the limit as n approaches infinity of 19 over n squared times n plus 1 over 2. Now, when you multiply across here, you know that you're going to have a 19n squared. You'd also have a 19n, but that is irrelevant in a limit as n approaches infinity. The only terms of relevance are the leading coefficients in front of the largest power of the variable. So I have a 19n squared in the numerator. My denominator would be a 2n squared. I know that as the limit as n approaches infinity of that, the n squareds would cancel and I'd have 19 over 2 left over, which should be my answer for 21. So I'll go in here and say 19 over 2, and we will check that answer now. And let's see here. Check answer. And correct. Next question. For this one, it's similar to the last one, except now I have 3 terms in the numerator. No big deal. What I know is I can distribute that denominator to each term in the numerator and create 3 separate summations from this. So if we have the limit as n approaches infinity of the summation from 1 to n of 3s to the second minus 4s minus 2 over n cubed, and s is going from 1 to n, then what I did is I just said, well, this first term divided by that, I could factor a 3 out of if I separated that individual term in the summation and have 3 over n cubed times the summation of s squared. Then I would have minus 4 over n cubed times the summation of s's. And then finally, minus 2 over n cubed. And if you factored out a 2 in that third summation, you just have a factor of 1 left on the inside. Now, when I simplify all 3 of these, the first one, the sum of the first n squared terms, well, by formula, n times n plus 1 times 2n plus 1, all over 6. The sum of the first n terms is n times n plus 1 over 2. And I know that the summation of 1 n times is just n. That's going to be 1 plus 1 plus 1 plus 1 n times, so I get the n there. Now, when we simplify that, this first fraction is going to give me 3 times 2n cubed for a total of 6n cubed, all over 6n cubed. Notice the rest of the terms in the numerator are completely irrelevant. They would be lower powers of n, thus they would be infinitely times smaller than that first term. Minus, I would have a 4n squared, and of course plus 4n. We don't put the 4n because it's irrelevant, all over 2n cubed. And then my last one, this n cancels out with one of the n's in the denominator, but we still are left with minus 2 over n squared. Now, when I'm looking at this, anytime the degree of the denominators exceeds that of the numerator and n is going to infinity, you know that that fraction is going to 0. So I'm just going to have 6 over 6 here for a 1, minus the second 2 fractions are just 0, so it should be 1 minus 0 minus 0. Should be a final answer of 1 here. We'll try 1 and check that answer. And it says wonderful. For 23. 23 is actually the first Riemann sum problem. I was running out of room on this page, so I just showed you for the basic cases, you don't even have to do a formal Riemann sum. It's just trying to find the area under the curve. So the only thing I did for this function f of x is equal to 6x, I said, since it's a basic problem, let's do the basic solution to it. I drew out my function 6x. We know at x equals 0, because we're trying to find the area from 0 to 5. At x equals 0, the y value is 0. At x equals 5, the y value would be 6 times 5, or 30. So the area under this curve is just the area of this triangle generated underneath it. So I just said 1/2 base times height, 1/2 5 times 30, and I got an area under this curve of 75, which should match the infinite Riemann sum approximating the area under that curve. So we say 75, check that answer, correct. Moving on. You're thinking, well, that one wasn't too fun. It was a little too straightforward. I agree. So let's look at this one. We could chicken out and do this one by geometry as well, but it specifically asks us to calculate the limit using a Riemann sum and then verify your answer, using geometry. Now, in this case, it's wanting the left-hand rectangle rule with infinitely many rectangles. I always prefer to use the right-hand rectangle rule because my summation formulas start at 1. They don't start at 0 like the left-hand rule starts at 0. So the only thing I did here is I just said, well, I know that the answer as n approaches infinity of the left-hand rule and the right-hand rule are the same. So why bother starting at 0 if we don't have to? No reason. I know that they give me the same answer, so I just said this is equal to this, which is equal to the limit as n approaches infinity of the summation from I equals 1 to n of f of a. Remember, a is just your beginning point, plus I times delta x. Delta x is just your change from one rectangle to the other. That's always b minus a over n, in this case 4 over n. And then all of that height function times delta x again. So in this problem, like I said, a is 0. Your delta x is 4 over n. We multiply that by I inside the function. And then times delta x, 4 over n. This 4 over n can and should be brought out in front of the summation. And then I have just f of 4i over n on the inside. When I plug that into the function, that's the next step. What is f of 4i over n? Well, you're plugging it in right here. It becomes 9 over 2 times 4i over n plus 4. Now, if I distribute on the inside, I'll get 36i over 2n plus 4. And then I'm going to separate that into two separate summations in this step. In my first one, this 36 over 2n can come out, and when it comes out, it reduces down to 18 over n times the summation of I. And the second one I just left alone, 4 over n times the summation of 4. Now, in that first one, we know by formula, the sum of the first n terms, 1 plus 2 plus 3 plus 4, that's what the I of that value is going to give you there. It's just equal to n times n plus 1 over 2. So I can say, okay, my first one is going to give me 4 times 18 over n squared, 72 over n squared times that summation formula. My second sum, that's the summation of 4. You're adding 4 to itself n times. That's where the 4n comes from. So I have 4 over n times 4n. Now, when we try to simplify these down, I see that that first one, I'm going to have a 72n to the second in the numerator, a 2n to the second in the denominator. The other terms in the numerator are irrelevant because they're lower powers of n. In the second term, my n's cancel out, and I would just have 4 times 4 is 16, so there's no n to worry about there. In the first one, 72n squared over 2n squared, the limit as n approaches infinity, that limiting value is just going to give you 36. We have 36 plus 16 is 52. That should be our answer. Now, it asks us to verify this with geometry, so I drew out the function 9 over 2 plus 4. At x equals 0, obviously the y value is 4. That's your y-intercept. When you plug a 4 into that equation, you get 9 over 2 times 4. Same thing as 9 times 2 is 18, plus 4 is 22. So this function is going to start at 0, 4. It's going to go to 4, 22. We need the area underneath it. So I said, well, the geometry, the area underneath the curve, it's going to be the area of a sub 1 plus a sub 2. I had to create two regular shapes that I could find the area for, so I separated it into a triangle and a rectangle. The base of that triangle is going to be 4, the height of it 18, so 1/2 4 times 18. Similarly, the rectangle has a base of 4 and also a height of 4. So 4 times 4 gives me the 16. Notice how that simplified out to be the exact same two components as my summation. 36 plus 16 both ways, and we get our answer of 52. Gorgeous. We put the 52 in there, check answer, yes. 25. So in 25, it's my first problem that a little bit more fun instead of just the basic linear functions. It gives me, in this one, f of x is equal to 12x quantity squared, which I just went ahead and simplified to 144x squared. And we're trying to find the area under the curve from -1 to 5 using this infinite approximation formula, Riemann sum. And in order to do that, I first found delta x. I said, well, delta x is the width of each rectangle inside of that. Always b minus a, 5 minus -1, which gives me a distance of 6. Divide that by the number of rectangles, n rectangles. So I get 6 over n, and this is going to be as n approaches infinity, so each of those rectangles become infinitesimally thin. They just become lines up to the curve. Our formula now for r sub n every single time is the summation from 1 to n of f of a, which that's just your beginning point, plus I times delta x. Delta x right here. So we're going to have 6i over n for that part, and of course times 6 over n. That's what I did in this step. So we have f of -1 plus 6i over n times 6 over n. This 6 over n could have been brought out in front. I didn't choose to do that in this problem. I left it as a factor on the inside temporarily. But what I did do in this step is I said f of -1 plus 6i over n. That's plugging it into the function. You'll have 144 times the group. Instead of x squared, it's -1 plus 6i over n quantity squared. Now what I did in this step is I factored out 144 times 6 over n. That gave me 864 over n. It gets pulled out on the front. And then I squared out that group. -1 plus 6i over n squared gives me -1 times -1 for 1, minus 6i over n, minus 6i over n for minus 12i over n. And then your last term is 6i over n squared, 36i squared over n squared. Now I see I have 3 separate terms inside the summation. I want to create 3 separate summations. And every single one of those summations are being multiplied by 864 over n. So I have 864 over n times the summation of 1, minus 864 over n times the summation of 12i over n, and then plus 864 over n times the summation of 36i to the second over n to the second. So now I can say, okay, this is looking pretty good at this point. I'll go ahead and bring out any terms I can. I know that the summations of 1, just n, it's the summation of 1 n times. This next one, this 12 over n comes out in front. It multiplies the 864 over n. And then the last one, the 36 over n squared gets pulled out front, multiplies the 864 over n. Now, for the next step here, what I did is I said, okay, 864 over n times n, the n's cancel, just gives me 864. The second one, 12 times 864, 10,368, and I'll have the n squared in the denominator. That's multiplying the summation of i's from 1 to n. By formula, that's n times n plus 1 over 2. And then plus, over here, the product of 864 and 36, 31,001 over 104 over n cubed. We're multiplying that by the summation of the I squareds, which is my n times n plus 1 times 2n plus 1 over 6. Now at that point, guys, it's pretty straightforward. You just say, well, okay, all of this is inside of a limit as n goes to infinity. So for all the rational expressions inside of this, I only need to know what are the leading coefficients in my numerator and denominator, and of course the power of n in each of those cases. So for this one, I'm going to have 10,368 times n squared, no other term matters, over a 2n squared inside of that limit, The last term, I'll have a 2n to the third times the 31,104. That's where the 62,208 n cubed comes from. The rest of the terms are irrelevant over your denominator of 6n cubed. Anytime the degree of the numerator and denominator is the same, you just take the fraction of the leading coefficients. So I'll have 864 minus 1,368 over 2 gave me 5,184. And 62,208 over 6 gave me 10,368. I subtract the second term, add the third term, and I get 6,048 for my solution. We'll check that with what achieved once. And we are correct. Moving on. So that was 25 for 26 here. It's a similar problem. We still have a x squared term in there, 16x squared minus 4. This time we're looking at finding the area between 2 and 5. So again, I find my delta x, b minus a over n, becomes 5 minus 2 over n for a delta x of 3 over n. My basic formula that says, well, it has to be f of the beginning point plus the change in x times I times the change in x becomes, in this case, f of the beginning point 2 plus 3i over n times delta x of 3 over n, all inside of this infinite summation. In this step, I go ahead and I pull the 3 over n out in front. And then after I pull that 3 over n out in front, I'll say, well, what is f of 2 plus 3i over n? Well, it becomes 16 times the group, 2 plus 3i over n squared minus 4. So now from this step to this step, I'm trying to algebraically simplify that. I still have my 3 over n out in front of the summation, and then times 16 times the group. I've just squared this out. 2 squared is 4. My middle term would be 2 times 3i over n plus 2 times 3i over n, 6i over n plus 6i over n for 12i over n. Your last term is 3i over n times itself for 9i squared over n squared. We still have the minus 4 in there. Now I'm trying to simplify that. I gather like terms. I'll have 16 times 4 is 64, minus 4 gives me the 60. I'll have 16 times 12i over n for 192i over n. I'll have 16 times 9i squared over n squared for 144i squared over n squared. So now at that point, I can come down here and say, well, I'm going to have, for this first term, I know that the summation of 60s, please again remember, that's just 60 plus 60 plus 60 plus 60 n times. So I'll say, well, okay, now what I chose to do that in 2 steps here. I could have just said 3 over n times 60n, but what I chose to do is I factored out the 60 first and then said times the summation of 1s, but that summations of 1s is just going to become an n in the next step. So whether you wanted to go ahead and get rid of that 60 and just say that's going to be 3 over n times 60n, or do it in 2 steps like I did here, either way, it's fine. In my next one, I had the 3 over n times 192 over n gets factored out of that, and I'll have the summation of i's left over. My last one, I'll have 3 over n times the 144 over n squared gets factored out, times the I squared left inside of the summation. So now, whenever I'm trying to simplify this out, I'll say, well, okay, my first one, I've already talked about that, about how the summation of 1 is going to become n. The summation of i's by formula, n times n plus 1 over 2. And the summation of I squareds by formula, n times n plus 1 times 2n plus 1 over 6. Now, what I've done from this step to this step, I said in this first one, I know those n's cancel. I just have 180. My second term, I said 3 times 192. Let's see, 3 times 192. That gave me the 576. But then I said, okay, I'm going to have 576 n to the second. No other term matters. All divided by 2n to the second. Well, that's just going to be 576 n to the second divided by 2n to the second. That's where the 288 came from there. And then in my last one, I would have 432 times a 2n cubed. Again, remember, no other power of n matters in that numerator because it's infinitely times smaller. I would have 864n cubed over a 6n cubed. Well, 864 divided by 6 simplified down to be 144. Add those three terms together, and I get my 612. We check that, and it is correct. We go to the next problem, 27. So in 27, again, we have a quadratic inside of this that we're trying to find the area underneath. This time 5x squared plus 35x, and we're trying to find the area using an infinite Riemann sum between 6 and 11. So then I can say, well, again, every single time delta x is going to be b minus a over n. Gives me 11 minus 6 over n, 5 over n in this problem. So my basic formula, which says f of the beginning point becomes f of 6 plus I times delta x becomes 5i over n times delta x, 5 over n. The 5 over n common width gets pulled out in front of the summation. And then I take the function of 6 plus 5i over n becomes 5 times that group squared plus 35 times that group. Now from this step to the next, I just algebraically simplified that. I'll have the 5 over n times the summation, 5 times this group squared. Well, 6 plus 5i over n squared becomes 36 plus 60i over n plus 25i squared over n squared. 35 distributes into the second group to give me these two terms. So now I'm collecting like terms. I said, well, let's collect the I squared terms. There's just the one of them. 5 times 25 I squared over n squared gives me 125 I squared over n squared. Then I collected the terms of I. I would have 300 I over n plus 175 I over n for a total of 475 I over n. And then the constants, you would have 5 times 36 is 180. 180 plus 210 for 390 there. So now I have three separate terms inside the summation. I want to make three separate summations. Your first summation, that 5 over n is going to get multiplied by 125 over n squared times the summation of I squared. Your second summation, 5 over n is going to get multiplied by 475 over n times the summation of the i's remaining inside of there. And then the last one, I just said, well, I know that the summation of 390 is just going to be 390n. It's 390 added to itself n times for 390n. Now, when we simplify this out, the limit as n approaches infinity, I multiplied this product to give me 625 over n cubed times the summation of I squared, which again, that's just by formula, n times n plus 1 times 2n plus 1 over 6. 5 times 475 gave me 2375 over n squared times the summation of I, which gave me the n times n plus 1 over 2 by formula. And I know in the last one, I just have the n's cancel, and I'll have 5 times 390. It's just going to be 1950, and I'll cancel those n's in the next step. So my first term, I would have 625 times 2n cubed. That would give me 1250 n to the third over 6 n to the third. That reduced down to 625 over 3. Then the second term here, I would have had 2,375 n to the second over 2 n to the second. Once you take the limit, it's 2375 over 2. And then we already discussed the last term is just the 1950 because the n's cancel. Whenever I added these together, and I also knew that Achieve said it wanted a fraction here. Actually, when I did this, my calculator would not do the fraction for me. Notice if I try to add these together, 2375 over 2 plus 1950, my calculator wouldn't give me the fraction. I hit the math, enter, and it's like leaving it as a decimal. Achieve doesn't want the decimal. You quickly realize, well, it's just a fraction with a 6 in the denominator. So what I did, the 0.833, recognizing that that's just 5 over 6, I multiplied this by 6, which then gives me my numerator, had to be 20,075 over 6. And that should be the answer that Achieves wants. 20,075 over 6. Check answer. Yes. Up next, probably the hardest one, and not that it's bad, but the hardest one in this section is probably 28. We have the group 4x cubed minus 4x, which I went ahead and cubed out that 4x cubed to give me the 64x to the third minus 4x. We're trying to find the area under this curve between 0 and 2. We know our delta x is going to be 2 over n. So then using that information, f of a plus I delta, well, your a in this case is just 0. So you just get f of 0 plus delta x times I, that's going to be 2i over n. That's where the f of 2i over n comes from, times delta x, 2 over n. So now you need to plug this 2i over n into your function here. That's where the 64 times 2i over n cubed minus 4 times 2i over n came from. Again, the 2 over n came out in front. Now, simplifying that down, this just became 8i cubed over n cubed multiplied by 64 gave me 512i cubed over n cubed. My second term just minus 8i over n. I knew I had two terms inside the summation. I was going to distribute into two separate summations, each one still multiplied by that 2 over n. I'll have 2 over n times 512 over n cubed times the summation of I cubed minus 2 over n times 8 over n times the summation of i's. So then at that point in the problem, I went ahead and multiplied out my first one to get the 1024 over n to the fourth. And then I know by formula, the summation of I cubed is the same thing as the summation of I, except it's quantity squared. So instead of n times n plus 1 over 2, it's n squared times n plus 1 squared over 2 squared, which is over 4. Minus 16 over n squared, that's the second product, times the summation of i's, which is n times n plus 1 over 2. So then I know in my first one, if I multiply all this out, I would get 1024 n to the fourth. And then, yes, there'd be a whole bunch of other terms, but those terms are irrelevant, divided by 4n to the fourth. My second, I would have 16n to the second over 2n to the second. And both of these are rational functions with the same degree in the numerator and denominator. So the limiting value as n approaches infinity is just the fraction of the leading coefficients. I'll have 1024 over 4. That gives me 256 plus 16 over 2, which is 8. 256 plus 8, 264. Should be the answer there. We check that. And, oh, let's see. Achieve is not liking it. Let's take a look here, guys. Ah, I see what it is. So one of the nice things about Achieve, and I'll pretend that I did that on purpose. I didn't, but let's pretend I made that mistake on purpose. One of the nice things about Achieve is that it's going to let you try as many times on these problems as you want. It'll give you a little hint about what you might have done wrong over on the right-hand side, though to me, the hints usually are not too helpful. But all you have to do is hit try again, and you can work the problems as many times as you want. So I'll say I made this mistake on purpose. Notice here at the very, very, very end of the problem, I was subtracting all along. And then for some reason, I put, instead of a minus, I put a plus here. Well, this is just going to be 256 minus 8 instead of 256 plus 8. The 256 minus 8 is going to give me the 248 instead of the 264. So 248, I'll check that answer. Correct. So I'll go back, and before I post this, I'll white out there. I already had to white out in this problem once, if you can kind of tell right there. But I'll white out that plus, put a minus, minus, and then a final answer of 248 there. So it just says solve correctly in 2 attempts. Does that any penalty as far as your final score? Absolutely not. And again, just pretend I made that mistake on purpose. The last one here, when we're looking at it, well, maybe, come on, there we go. When I'm looking at it, it's asking me to express f of x is equal to 7 sine x over the interval 0 to pi over 4 as a limit. So it's giving you a multiple choice answers here, and I've accidentally selected one, but I haven't saved it, so that's okay. But when we're looking at how to work this, the way I thought about it is as follows. Here's your function, the interval that we're trying to find the area under. So of course your delta x is always b minus a over n. So pi over 4 minus 0 over n, that just becomes pi over 4n. That's your delta x. So now in your function, it is always f of a plus, I always say I times delta x, but they're using j as the index here. So it's f of a, which is 0, plus j delta x, which is pi times j over 4n, times your delta x, pi over 4n. So now this is going to become the summation from j equals 1 to n. Well, what is f of pi j over 4n? That just takes the place of x inside of your function. So you have 7 sine of the angle pi j over 4n times that common width of the rectangles, pi over 4n. Now, in order to match their answers, they're wanting you to leave everything on the inside of the summation, but you can multiply the two constant factors. The only variable term is this right here with a j in it. This 7 pi over 4n could be multiplied, and I'll bring it out front to match their ordering, times the sine of that angle, pi j over 4n. So now it's just a matter of matching that with one of their multiple choice selections. I have 7. Now, please do remember, right-hand rules always start at 1 and they go to n. A lot of these values, like the one I currently have selected, there's no way that's the right answer. That's a left-hand rule. So I don't want it to go to n minus 1. The first two automatically cannot be. Could be the third one, but actually it can't be because notice it has the wrong fraction in front. It has to be 7 pi over 4n. So it's not the first three, it's not the fourth one, it has to be the fifth one. It goes from 1 to n of 7 pi over 4n, sine of pi j over 4n. Gorgeousness, oh gorgeousness. Yes. Okay, so hopefully this has helped you out with this first homework assignment for section 5.1 on Achieve. I will continue to do this throughout the entire class, hopefully helping you out when you have any questions with any of the problems. Let me know if there's any other way I can help you. I'll be glad to do whatever I can.